a guitar string, a satellite, a shadow at noon, the electricity in your wall, a heartbeat on a monitor, and a ramp outside a building. 6 things that have nothing to do with each other, except that they are the same thing. And the object that connects all 6 is the simplest shape, one radius sweeping around, and 2 numbers that describe where the tip of that radius is at every instant. Those 2 numbers are called cosine and sine, and once you understand them, all 6 of those pictures become one picture. We are going to build trigonometry from absolutely nothing. No memorizing, no magic tables. We start with a triangle you could draw with a stick in the sand, and we finish at the equation that physicists call the most beautiful in mathematics. Every single step in between, you will see. This is trigonometry, not the version that made you memorize a table for a test. The version that runs your phone, your music, your electricity, and every animated frame you have ever watched. Start with the simplest interesting shape in geometry, a right triangle. One corner is a perfect square corner, 90 degrees. Pick one of the other 2 corners and call its angle theta. That single angle is about to control everything. Now watch what happens when I make the triangle bigger, not stretched, scaled. Every side grows by the same factor, and the angles stay exactly where they were. This is the oldest theorem in the toolkit, similar triangles. Here is the consequence, and it is the most important sentence in this entire video. When the triangle grows, the sides all change, but the ratio between any 2 sides does not change at all. Divide the tall side by the long side, and you get the same number for the small triangle, the big triangle, and every triangle in between. So the ratio does not depend on the size of the triangle. It depends on one thing only, the angle. Change the angle, the ratio changes. Keep the angle, the ratio is locked, which means we can stop thinking about triangles and start thinking about a machine. You feed in an angle, and out comes a number. Before we name the machines, we need names for the sides. The longest side, always opposite the right angle, is the hypotenuse. The side directly across from theta is the opposite, and the side touching theta, that is not the hypotenuse, is the adjacent. Opposite and adjacent swap. If you switch to the other corner, the hypotenuse never moves. 3 sides means 3 obvious ratios, and each one gets a name. Opposite over hypotenuse is the sine of theta. Adjacent over hypotenuse is the cosine of theta. And opposite over adjacent is the tangent of theta. That is the whole of basic trigonometry, right there in 3 lines. Generations of students have remembered this with one nonsense word, SOH CAH TOA. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. It is silly and it works, and you will never forget it. Let us actually use it. Here is a triangle with sides 3, 4, and 5, the most famous right triangle there is. The angle theta sits at the corner where the 4 and the 5 meet. Opposite theta is 3. Adjacent is 4. Hypotenuse is 5. So sine of theta is 3/5, or 0.6. Cosine is 4/5, 0.8. And tangent is 3 over 4, 0.75. And here is the check that proves the point about similarity. Double every side, 6, 8, 10. Recompute. 6 over 10 is still 0.6. 8 over 10 is still 0.8. The triangle changed, the angle did not, the answers did not. There are 3 more functions, and they are not new, they are just these 3 flipped upside down. 1 over sine is cosecant, 1 over cosine is secant, and 1 over tangent is cotangent. The annoying part is that cosecant pairs with sine and secant pairs with cosine, which feels backwards to everybody. It is a historical accident. Blame the 16th century. So where did these names come from? Not from triangles. Trigonometry was not invented by builders. It was invented by astronomers, more than 2,000 years ago, trying to predict where the planets would be. Around 150 before the Common Era, a Greek astronomer named Hipparchus needed a way to turn angles in the sky into distances, and he built the first trigonometric table in history. But Hipparchus did not use sine. He used something called the chord, the straight line joining 2 points on a circle. 300 years later, Ptolemy pushed the same idea into a table so precise it went in half-degree steps, and stayed in use for over 1,000 years. For most angles, sine and cosine are ugly infinite decimals that you need a calculator for, but for a handful of special angles, The answers are exact and beautiful, and you can derive every one of them yourself from two shapes you already know. Take a square with sides of length 1 and cut it corner to corner. You now have a right triangle with two 45-degree angles. Both legs are 1, and by Pythagoras, the diagonal is the square root of 2. So for 45 degrees, sine is opposite over hypotenuse, which is 1 over root 2. Cosine is adjacent over hypotenuse, also 1 over root 2. Identical, because the triangle is symmetric. And tangent is 1 over 1, which is exactly 1. Now the equilateral triangle, all sides length 2, all angles 60 degrees. Drop a line straight down the middle. It splits the bottom side into two halves of length 1, and it splits the 60-degree angle at the top into two 30-degree angles. You have just built the 30-60-90 triangle, and its height, by Pythagoras again, is the square root of 3. From that one triangle, you get four values at once. Sine of 30 is 1/2. Cosine of 30 is root 3 over 2. Sine of 60 is root 3 over 2. Cosine of 60 is 1/2. Notice the pattern. 30 and 60 have swapped answers because they are the two angles of the same triangle. And now the trick that makes all of this memorable. Write the numbers 0, 1, 2, 3, 4 in a row. Take the square root of each. Divide each by 2. You have just written the sign of 0, 30, 45, 60, and 90 degrees in order. Read the same row backwards, and you have the cosines. The tangent row you can fill in yourself, because tangent is just sine divided by cosine. 0, root 3 over 3, 1, root 3, and then at 90 degrees something breaks. Cosine is 0, and you cannot divide by 0. Tangent of 90 degrees does not exist. Hold on to that. We will come back to it with a vengeance. There is one more relationship hiding in this table. Sine of 30 equals cosine of 60. Sine of 60 equals cosine of 30. In general, the sine of any angle equals the cosine of 90 minus that angle. That is the co in cosine. Co means complementary. With just these values, you can solve real problems. Here is a classic. You stand 50 meters from a tower. You look up at the top, and the angle above horizontal is 30 degrees. How tall is the tower? The height is opposite the angle. The 50 meters is adjacent. Opposite over adjacent is tangent. So tangent of 30 equals height over 50. Tangent of 30 is root 3 over 3, about 0.577. Multiply by 50, and the tower is about 29 meters tall. You just measured a building without touching it. Now a problem. Everything so far lives inside a right triangle, and a right triangle has a hard limit. The other two angles must add to 90 degrees. So every angle we can talk about is between 0 and 90. What is the sine of 120 degrees? With triangles, the question is meaningless. There is no such triangle. So we need a bigger home for these ideas. Something that does not care about 90 degrees, or 180, or 1,000. And the answer has been sitting in this video since the first minute. This is the unit circle. Center at the origin, radius exactly 1. Draw a radius out to any point on it, and measure the angle from the positive horizontal axis, going counterclockwise. Now drop a vertical line from that point down to the horizontal axis. Look what appeared, a right triangle, and its hypotenuse is the radius, which is 1. Here is where it becomes elegant. Sine is opposite over hypotenuse, but the hypotenuse is 1, so sine is just the opposite side. Cosine is adjacent over hypotenuse, again divided by 1, so cosine is just the adjacent side. The vertical leg is the sine. The horizontal leg is the cosine, which means the point on the circle sits at coordinates cosine theta, sine theta. So sine and cosine stopped being ratios of sides. They became coordinates. Cosine is how far right you are. Sine is how far up you are. And unlike a triangle, a coordinate does not care how big your angle is. Now let the angle keep going. Past 90 degrees, into the top left. Past 180, along the bottom. Past 270, and back around to the start. The triangle definition died at 90 degrees. The coordinate definition never even blinks. In quadrant 2, x is negative and y is positive, so cosine is negative and sine is positive. In quadrant 3, both are negative. In quadrant 4, x is positive and y is negative, so cosine is positive and sine is negative. You do not memorize this. You just read the signs off the axes. If you want the shortcut, the 4 quadrants spell out which functions are positive, All, sine, tangent, cosine. Some people remember it, as all students take calculus, but please remember the reason as well as the rhyme. The reason is just the sine of x and the sine of y. There is one more tool, the reference angle. Take any angle at all, and measure the acute angle between its radius and the horizontal axis. That is the reference angle. The size of the answer always comes from the reference angle. The sine always comes from the quadrant. 210 degrees has a reference angle of 30, and it sits in quadrant 3, so its sine is -1/2. Now we need to talk about how we measure angles at all. Degrees are arbitrary, 360 of them in a circle, because Babylonian astronomers 4,000 years ago liked the number 60, and there are roughly 360 days in a year. It is a historical convention, not a mathematical truth. Mathematics prefers a unit that comes from the circle itself. Take the radius and bend it around the edge of the circle like a piece of wire. The angle it sweeps out is 1 radian. That is the entire definition. 1 radian is the angle where the arc length equals the radius. Keep wrapping. 3 radius lengths fit around, and then a little more, about 0.14 more, which should sound familiar. It takes exactly 2 pi radius lengths to wrap all the way around a circle, because the circumference is 2 pi r. So a full turn is 2 pi radians, half a turn is pi, a quarter turn is pi over 2. Converting is easy. Pi radians equals 180 degrees. So to go from degrees to radians, multiply by pi over 180. To go the other way, multiply by 180 over pi. 30 degrees is pi over 6. 45 is pi over 4. 60 is pi over 3. Why bother? Because radians make the mathematics honest. Arc length is simply the radius times the angle in radians, no conversion factors. Later, when we do calculus, the derivative of sine is cosine only if the angle is in radians. In degrees, you pick up an ugly constant that never goes away. Radians are not a harder unit. They are the correct one. Radians also let us do something impossible with degrees. Take the number line, all the real numbers, and wrap it around the circle. Every real number now lands on a point, which means sine and cosine are not really about angles at all. They are functions of any number you like. And that overlap is periodicity. Going around once brings you back to exactly where you started. So sine of theta plus 2 pi is sine of theta. Add another 2 pi, same answer. Subtract 2 pi, same answer. These functions repeat forever, and their period is 2 pi. The circle also hands you the symmetries for free. Reflect a point across the horizontal axis, and the x-coordinate is unchanged, while the y-coordinate flips. So cosine of minus theta equals cosine of theta, and sine of minus theta equals minus sine of theta. Cosine is an even function. Sine is an odd one. And now the single most useful identity in all of trigonometry, and it costs us nothing. The point sits on a circle of radius 1. Pythagoras, on that little triangle, says the horizontal leg squared plus the vertical leg squared equals the hypotenuse squared. The legs are cosine and sine. The hypotenuse is 1, so cosine squared plus sine squared equals 1. Always. For every angle, that one identity has 2 children, and you get them for free. Take cosine squared plus sine squared equals 1, and divide every term by cosine squared. You get 1 plus tangent squared equals secant squared. Divide the original by sine squared instead, and you get cotangent squared plus 1 equals cosecant squared. 3 identities, 1 circle. These are the Pythagorean identities, and they are the workhorses. Anytime you see a squared trig function in a problem, one of these 3 is usually the way out. So where is tangent on this circle? Sine is a vertical length. Cosine is a horizontal length. Tangent is sine over cosine, which is rise over run. Which is slope? The tangent of the angle is exactly the slope of the radius line. But tangent also has a picture of its own, and it explains the name. Draw a line that just touches the circle at the point where the angle starts. A tangent line. Extend the radius until it hits that line. The length you have to travel up the tangent line, from the touching point to the crossing point, that length is the tangent. And the piece of the radius line from the center out to that crossing point, that is the secant. Secant means cutting. It is the line that cuts through the circle. Do the same construction against the horizontal tangent line at the top, and you get cotangent and cosecant. All 6 functions are line segments in one diagram. Look at what the picture tells you before you calculate anything. Sine and cosine are chords of a circle of radius 1, so they can never exceed 1. But tangent, secant, and cosecant are segments outside the circle. They have no ceiling at all. They run away to infinity. So we have a point going round a circle, and two numbers describing it. The last step is the one that changes everything. Instead of watching the point, we are going to watch just its height, and we are going to plot that height against the angle as time goes by. As the point climbs, the trace rises. At 90 degrees the point is at the very top, and the trace hits 1. Coming back down through 180, the trace returns to 0. Into the bottom half, the height goes negative, bottoming out at -1 at 270, and then back to 0. That shape has a name, and you have seen it your entire life. Keep going, and it does it again. The circle is the machine, the wave is the printout. Every wave you have ever seen, sound, light, water, electricity, is something, somewhere going round in a circle. Now do the same thing with the horizontal position instead of the vertical. You get the same wave, but it starts at 1 instead of 0. That is the cosine. Sine and cosine are the identical shape, just a quarter turn out of step with each other. That quarter turn offset has a name, phase. Sine and cosine are 90 degrees out of phase. It is the same reason the pedals on a bicycle are opposite each other. Same motion, same speed, different starting point. Now the tangent graph, and this one behaves badly. Tangent is sine over cosine. Wherever cosine is 0, we are dividing by 0, and the graph explodes. Cosine is 0 at 90 degrees, at 270, and every 180 degrees after that. So the tangent graph is cut into pieces by invisible walls. And notice something odd. Tangent repeats every 180 degrees, not 360. Its period is pi, not 2 pi. That is because a slope does not care which end of the line you are on. Rotate a line halfway round, and the slope comes back to exactly where it was. That is the same explosion we found in the special angle table, when tangent of 90 degrees came out undefined. Now you can see what undefined actually looks like. It is not a hole. It is a cliff. The reciprocal functions get graphs too. Cosecant is 1 over sine, so wherever sine touches 0, cosecant blows up. Its curve sits in a nest of U-shapes tucked inside the sine wave. Secant does the same thing to cosine. Cotangent is tangent flipped, sloping downward instead of up. Now let us take control of the wave. The general form is y equals a times sine of bx plus c plus d. 4 numbers, 4 knobs, and each one does exactly one thing. And the best part is that each knob is a physical change to the circle that made the wave. A is the amplitude, how tall the wave is. And on the circle, it is simply the radius. Make the circle bigger, and the wave gets taller, because the point is climbing higher. Amplitude 3 means the wave swings from +3 to -3. B controls the period, how stretched or squashed the wave is. On the circle, B is the spin speed. Double B and the point goes round twice as fast, so you fit 2 full waves in the same space. The period is 2 pi divided by B. C is the phase shift, a head start. On the circle, it is where the point was standing when the clock started. And here is the trap that catches everybody. The shift is not C. It is -c over B, because the B is multiplying the x before the C ever gets added. And D just lifts the whole thing up or down. It is the midline, the level the wave oscillates about. On the circle, it is simply moving the circle's center. Amplitude, period, phase, midline. 4 knobs, and you can build any sine wave that exists. In physics and engineering, B has its own name, angular frequency, written omega. It is how many radians the point turns through per second. Divide it by 2 pi, and you get frequency in cycles per second, hertz, which is exactly how we describe a musical note, a radio station, and the electricity in your wall. So the wave is not a picture of a wave. It is a picture of a rotation, seen from the side. Stand at the edge of a merry-go-round and watch a rider go past. They do not look like they are going round. They look like they are sliding back and forth. Same motion, different viewpoint. That shadow of circular motion has a name, simple harmonic motion, a mass on a spring, a pendulum with a small swing, a vibrating molecule. All of them trace a sine wave in time, because all of them are, mathematically, the shadow of something going round. And that is the whole reason trigonometry escaped from geometry. Every question so far has been, here is the angle, what is the ratio? The far more useful question in real life is the opposite. Here is the ratio, a slope, a height, a distance. What is the angle? For that, we need to run the machine backwards. But there is an immediate problem. Suppose the sine is 1/2. Which angle is it? 30 degrees works. So does 150. And so does 30 plus a full turn. And 30 plus 2 full turns in both directions. There are infinitely many correct answers. A function is only allowed one output per input. So mathematicians made a decision. Pick a slice of the sine wave that goes up exactly once, hitting every value from -1 to 1, and throw the rest away. That slice runs from -90 degrees to +90. Inside it, every value has exactly one angle. That restricted slice can be flipped to give the inverse sign, also written arcsine. Reflect the curve across the diagonal line y equals x, and there it is. Its inputs run from -1 to 1, and its outputs run from -90 to +90 degrees. Cosine gets the same treatment, but its slice runs from 0 to 180 degrees, because cosine starts at the top and comes down, so that is where it passes each value exactly once. An arctangent takes the branch between -90 and +90, but it never reaches them. It flattens out and approaches them forever. Now the notation warning, and it matters. Inverse sine is often written as sine with a superscript -1. That does not mean 1 over sine. 1 over sine is cosecant, which is a completely different function. Sine to the power -1, in this one context, means the inverse. It is bad notation that we are stuck with, so write arcsine when you can. Here is the inverse in action. A ramp rises 1 meter over a horizontal run of 12 meters. What is its angle? Rise over run is opposite over adjacent, which is tangent. So tangent of the angle is 1 over 12. Arctangent of that is about 4.8 degrees, which happens to be just inside the legal limit for a wheelchair ramp in most building codes. There is one more wrinkle, and if you write code you will meet it. Arctangent only knows the ratio y over x, but -1 over -1 gives the same ratio as 1 over 1. So arctangent cannot tell quadrant 1 from quadrant 3. It guesses, and half the time it is 180 degrees wrong. Which is why nearly every programming language has a second function called atan2. You hand it the y and the x separately instead of pre-divided, so it can see both signs and give you the correct angle in all 4 quadrants. If you have ever made anything on a screen point towards something else, you have used it. Suppose you know the sine of 30 and the sine of 45. What is the sine of 75? The tempting answer is to add them. The tempting answer is wrong, and it is wrong by a lot. Sine is not linear. You cannot break an angle apart and add the pieces, but there is a formula that does it properly, and it is the most important identity in the subject, because it is really a statement about combining 2 rotations into one. Here is the classic construction. Draw a right triangle with angle A sitting on the horizontal. On its hypotenuse, build a second right triangle with angle B. Make the outer hypotenuse exactly 1 unit long. The total angle from the horizontal to that outer edge is a +b. Now find the height of the outer tip. In the small upper triangle, the hypotenuse is 1 and the angle is b, so its vertical side is sine b and its horizontal side is cosine b. Then carry those 2 lengths down through the lower triangle, which is tilted by a. The cosine b piece, tilted by a, contributes a height of sine a times cosine b. The sine b piece, also tilted, contributes a further cosine a times sine b. Add them, and the total height of the tip is sine a cosine b plus cosine a sine b. But the tip is on a unit length line at angle a +b, so its height is simply the sine of a +b. Run the same argument horizontally, and you get the cosine version, with one surprise. The 2 horizontal contributions pull in opposite directions, so they subtract. Cosine a cosine b minus sine a sine b. That minus sign is not a typo, and it catches people forever. The subtraction versions come free. Replace b with minus b. Remember that cosine is even and sine is odd, and every sign that touches a sine flips. That gives you sine a cosine b minus cosine a sine b, and cosine a cosine b plus sine a sine b. And there is a deeper way to see all of this. Rotating a point by angle, and then by angle b, is the same as rotating it by a +b in one go. Write those rotations as matrices, multiply them, and the angle addition formulas fall straight out of the arithmetic. The identity is not a trick. It is what rotation is. Tangent has its own version. Tangent A plus tangent B, all divided by 1 minus tangent A times tangent B. It comes straight from dividing the sine formula by the cosine formula, then dividing top and bottom by cosine A cosine B. Now set B equal to A, and something wonderful happens. The addition formula becomes a doubling formula. Sine of 2 theta is 2 sine theta cosine theta. That single line is used in physics, computer graphics, and signal processing constantly. Cosine of 2 theta has 3 faces: cosine squared minus sine squared, straight from the formula. Then use the Pythagorean identity to swap out either term, and you get 2 cosine squared minus 1, or 1 minus 2 sine squared. Same fact, 3 costumes, and which one you use depends entirely on what you are trying to cancel. Turn the last one inside out, and you get the half-angle formulas. Cosine squared theta equals 1 plus cosine 2 theta over 2. Rearranged, they let you find the sine or cosine of half an angle, which is exactly how the old astronomers extended their tables. Start with known angles, have them again. There is one more family, and it used to be the most valuable mathematics in Europe. The product to sum formulas turn a multiplication of 2 trig functions into an addition. Before logarithms existed, astronomers used these to multiply enormous numbers by looking up signs and adding them instead. The technique was called prosthaphoresis, and it saved years of human life. And that formula is not a museum piece. It is why, when 2 instruments play almost the same note, you hear a slow throbbing. 2 nearby frequencies added together equal 1 average tone, multiplied by a slow envelope. Musicians call it beating, and they use it to tune. Here is the last identity, and it is the doorway to everything modern. Take any sine wave and any cosine wave of the same frequency, with any amplitudes at all, and add them. You do not get a mess. You get a single, clean sine wave with a new amplitude and a new phase. Sines and cosines of the same frequency always combine into one sine, which means the whole family of same frequency waves is described by just 2 numbers, a size and a phase. That fact is the foundation of signal processing, of electrical engineering, and of the Fourier transform. That is the toolkit: Pythagorean, addition, double, half, product to sum, and harmonic. Every other identity you will ever meet is built from these. We have been assuming a right angle this whole time. Most real triangles do not have one. A plot of land, a truss in a bridge, 3 cities on a map, none of them are polite enough to contain a 90-degree corner. So we need tools for any triangle at all. The first tool is the law of sines, and the proof is one line of geometry. Drop a perpendicular from the top vertex to the base. That height can be computed 2 different ways, using the angle on the left or the angle on the right. Set the 2 expressions equal, and the law falls out. So in any triangle, each side divided by the sine of its opposite angle gives the same number. And that number is not random. It is the diameter of the circle that passes through all 3 corners. Use it when you know 2 angles and a side, or 2 sides, and an angle opposite one of them. But that second case has a trap. Sine of 130 degrees equals sine of 50. So when you take an inverse sine, there may be a second, obtuse triangle that fits your data just as well. The second tool handles the cases the law of sines cannot: 3 sides, or 2 sides with the angle between them. It is the law of cosines. C squared equals a squared plus b squared, minus 2 a b cosine c. And if you look at it for a second, you will recognize it. Because when angle C is 90 degrees, cosine of 90 is 0, the correction term vanishes, and you are left with exactly Pythagoras. The law of cosines is Pythagoras, generalized, with a term that measures how far from a right angle you are. And a bonus: the area of any triangle is 1/2 a b sine c, half the product of 2 sides, times the sine of the angle between them. It is the familiar half base times height, with the height replaced by what the sine tells you it must be. These 2 laws are how the world was mapped. Long before satellites, surveyors measured one baseline carefully, then measured angles to a distant landmark from both ends, and computed the distance they could never walk. Chain those triangles across a country, and you have a map. It is called triangulation, and entire continents were surveyed this way. The same trick measures the stars. Observe a nearby star in January, then again in July, from opposite sides of Earth's orbit. The star shifts against the background by a tiny angle. One baseline, one angle, and trigonometry gives you a distance in light years that no one will ever travel. One last generalization worth knowing exists. On a sphere, none of this quite works. The angles of a triangle no longer add to 180 degrees. There is an entire parallel subject, spherical trigonometry, and it is the one Hipparchus actually needed. It is what navigators and astronomers used for 2,000 years, and it is what your phone quietly uses to find your position on a round planet. But everything on that sphere is still built from the same 6 functions we defined at the start. Start with sound. A pure tone, a tuning fork, a test tone, is literally a sine wave of air pressure. How often it repeats sets the pitch. How tall it is sets the loudness. The note A above middle C is a sine wave that repeats 440 times every second. But a violin and a flute playing that same A do not sound the same, even though the pitch is identical. The difference is what else is in there. On top of the 440, there are quieter sine waves at 880, at 1320, and higher, the harmonics. The recipe of harmonics is what your ear hears as the character of an instrument, which leads to one of the great results in mathematics. Fourier proved that any repeating signal at all, however jagged, however strange, can be built by adding up enough sine waves. Not approximately, exactly. A square wave, a sawtooth, a spoken word, a piece of music, all of them are sums of circles going round. And that is not a curiosity. It is infrastructure. Every audio file, every image compression format, every wireless signal works by breaking a signal into sine waves, throwing away the ones you cannot perceive, and rebuilding it. The compression on the video you are watching right now is doing exactly this. Now the electricity in your wall. In a power station, a coil of wire spins inside a magnetic field. The voltage it produces depends on the angle of the coil, so the voltage it produces is, by definition, a sine wave. The mains is not sinusoidal by choice. It is sinusoidal because a generator is a thing that rotates. Rotate that idea faster, and you get radio, microwaves, light itself, all of them oscillating fields, all described by sines and cosines, all distinguished only by how fast they repeat. Change the amplitude over time, and you have AM radio. Change the frequency, and you have FM. Change the phase, and you have the digital signal carrying this video to you. Every frame of every game and animated film runs on this too. Rotating an object means multiplying its points by a matrix full of sines and cosines. Making something orbit, bob, sway, or pulse means driving its position with a sine. Even the way light falls on a surface is computed from the cosine of the angle between the light and the surface. Now the fact that makes calculus possible. Take a very small angle in radians and compare the arc, the chord, and the height. As the angle shrinks, all three become indistinguishable, which means for small angles, the sine of theta is approximately theta itself, and that approximation only works in radians. From that one limit, the derivative of sine turns out to be cosine exactly. The slope of the sine wave at every point is the height of the cosine wave at that point. Where sine is at its peak, its slope is 0, and cosine is 0 there too. It matches everywhere. Differentiate again, and cosine becomes minus sine. So sine is a function whose second derivative is its own negative. That single sentence is the equation of every oscillation in physics: springs, pendulums, circuits, atoms, waves. Ask nature what oscillates, and the answer comes back: sine and cosine and nothing else. So how does a calculator actually compute a sine? Not from triangles. It uses an infinite series. Theta minus theta cubed over 6, plus theta to the 5th over 120, and so on. Remarkably, that series was discovered in India by Madhava of Sangamagrama around 1400, roughly 250 years before Newton. Although in actual hardware, many devices use something even more elegant. An algorithm called SOH, invented in 1956 for aircraft navigation computers. It computes sines using nothing but addition, subtraction, and bit shifts, by rotating a vector in a series of ever smaller pre-computed steps until it lands on the angle you asked for. And finally, the deepest statement of all. Euler showed that e to the power I theta equals cosine theta plus I sine theta, which says sine and cosine are the shadows of a single object spiraling through the complex plane. Put theta equal to pi, and you get e to the I pi plus 1 equals 0, 5 fundamental constants in one line, and it is nothing more than the statement that half a turn lands you at -1. So, the guitar string, the satellite, the shadow, the socket, the heartbeat, and the ramp. 6 strangers at the start. Every one of them is a point going round a circle, and sine and cosine are just the two numbers that say where it is. Trigonometry is not a list of formulas to survive. It is one idea stated once, rotation measured in 2 directions. Everything else in this video, every identity, every graph, every law is a consequence of that. Thanks for watching all the way to the end.